So, hello to everyone who's watching online. Uh, since no one has joined the session in person yet, maybe I'll wait for 10-15 minutes before starting the session. So, I'll be starting in like 10 or 15 minutes, depending on if people show up for the session in time, in person. Till then, I'll just mute myself. Okay, since no one has joined the session in person yet, I guess we'll get started nonetheless. So, hello everyone who's watching on YouTube. Just to reintroduce myself, I'm Lakshay Saggi, the problem solving TA for the NPTEL Selected Topics in Algorithms course for the Tuesday 6 to 8 p.m. sessions. So sorry, my camera is not working today, so yeah, I won't be able to turn on my video right now. But yeah, so this is going to be the problem solving session for the fourth week, and in this session we'll be essentially discussing the uh, we'll be essentially recapping what was discussed in this week's lectures, and also we'll be discussing some problems related to uh, this week's content, so that uh, we can have a better idea of how to solve these assignments. And once again, like as I always say, that I'll be assuming that you guys have gone through the lecture videos, the NPTEL lecture videos, because these problem solving sessions are in no way substitutes for the official lectures, because yeah, one can't cover as much content in just 2 hours as much can be covered in like 1 week worth of lectures. So yeah, and this week the main topics which were discussed were essentially uh, so concentration bounds and uses of concentration bounds in various kinds of problems. And yeah, so we'll be recapping some of those. So let me just share my screen, guys, so that yeah, we can get started. I'll just share my screen now. Okay, so I hope my screen is visible to everyone. Yeah. No one is there in session to in person to confirm that, so I'll just have to assume that my screen is visible to everyone. So yeah, so let's get started. So this is week 4, and so let's just start with some recap. So in this week, the main idea was trying to apply the concentration bounds which we learned in week 3 to various kinds of problems. And for example, one of the most famous problems is one of the most famous problems in this regard is the coupon collector problem. So suppose the problem essentially is that suppose there is a bag with n coupons, and we pick a coupon uniformly randomly from the bag, we observe it and then put the coupon back into the bag. So we are kind of selecting the coupon, and but we are putting it back down. So we are not choosing without replacement, we are choosing with replacement here. And now the question is how many draws are needed to see all the coupons? So in how many draws will we be able to say that we have seen all the coupons? And um, this was discussed in the lecture that expected number of coupons which one needs to uh, pick are approximately n log n. And it was also shown in the lectures, you can show that using Markov's inequality that the probability that the number of trials that you need is greater than 2 n log n is less than equal to half using Markov bounds, and the probability that the number of coupons you need is greater than 2 n log n. The probability of this can be improved to order of 1 by log square n using Chebyshev bounds. And in fact, using just union bounds, we can show that actually the probability is even lower, which is just 1 by n. Essentially, the probability that the number of coupons which you need will be more, the number of coupons which you need will be greater than 2 n log n is like very small because n is usually chosen to be large. So yeah, so approximately you'll always be needing around n log n draws to uh, take out the best coupon. To take out to have to see all the coupons, you'll be needing around n log n uh, draws. And then the second problem which was discussed in this week was the birthday paradox problem. So what's the birthday paradox problem? Suppose there are n people in a room and their birthdays are distributed uniformly randomly into m days of the year. So there are 365 days, but let's just generalize the problem to, let's say, m days. So suppose a year has m days, and now there are n people and their birthdays are distributed uniformly randomly in across these m days. So now for what value of n, the probability that two people have the same birthday is at least half. So essentially, like, how many people do I need to select so that I can confidently say that uh, there exist two people who have the same birthday. So if the probability is at least half, so essentially I'm saying with a fair bit of confidence that there will exist at least two people in this bunch of people who share the same birthday. And it is intuitive that the more number of people you select, suppose you select m people altogether, then it's obvious that m plus, let's say you select m plus one people altogether, then it's obvious that by Pareto principle, at least on one day, two people will be having their birthdays. But actually, since these birthdays are distributed uniformly randomly, you can actually show a much smaller bound that you'll actually need just approximately root n people to ensure that two people have the same birthday. And the argument was discussed in the lecture, so it's how on a high level, how does the argument go? So uh, essentially in the argument, what we say is suppose someone tries to bound the probability that given n people, all of the n people have birthdays on different days, then the probability for this can be bound by this quantity 1 minus 1 by m, 1 minus 2 by m till 1 minus n minus 1 by m. So this is very easy to see that yeah, it's not too hard to see how this expression comes, and yeah, you can see this from the lectures also, and hmm. This actually resolves to e to the minus n square over m, which will be at most 1 over e for if we assume n to be around root n. Using some math here, like we can show that. Uh, yeah, for around n equal to root m, uh, we'll be having uh, this kind of scenario that the probability that two people uh, do not share same birthday is quite small. So this is the probability that everyone has a distinct birthday, and this is quite small for n equals to root m. So for n greater than equal to root m, the probability that at least two people have the same birthday is at least half. So yeah. So this is what is called the uh, birthday paradox problem, and yeah, on a high level, like I think you can see where this one come from, because suppose there are n people, so first person can have birthday on any day, but now you want the probability that also all the people have different birthdays. Then the second person should not have the birthday on the same day as the first person. So out of m days, the second person can not have birthday on this day, on which the first person had the birthday. So now the probability that the birthday lies on some other day for the second person will be 1 minus 1 by m. And now the third person, which we see, should not have the birthday on any of the 2 days which we have selected for first and second person respectively. So now the probability that the third person has a distinct birthday will be 1 minus 2 over m, and we can continue this till then nth person, and this will be like 1 minus n minus 1 over m. And since these are independent events, we can multiply their probability. And this is how we arrive at the answer. So, yeah. So this is somewhat interesting that if you were only allowing deterministic, like if you wanted to ask for worst case scenario, then it can happen that it might happen that you need to select m plus one people at least to ensure that two people have the same birthday, because in any group, so you can always select m group of people and you can assign all of them different birthdays, and then what happens is yeah, you can always have an assignment in which m people always have different birthdays, but with m plus one people, like always at least two people will have the same birthday. So in deterministic setting, you will need like at least m plus one people. But here we are talking about probabilities and randomization. So with high probability, you can say if the birthdays are uniformly distributed, then if you take, let's say, root n people, in those root n people only, you will be able to find at least, in the group of root n people, you will be able to find at least two people who share the same birthday. And then moving on to another application which was discussed in the lecture was the balls and bins problem. Essentially, the problem was suppose n balls are thrown independently into n bins uniformly randomly. So we have n balls and we throw them uniformly randomly and independently into n bins. And then what's the load of a bin? Load of a bin is just the number of balls in the bin. And now the question asks us that what is the maximum what is the maximum load uh, in, in the bin? So since the balls are thrown independently and with some and uniform randomly, so this maximum load won't be a fixed quantity. Of course, this will be also a random variable. So we are kind of interested in asking like maybe what's the expectation of the maximum load and like with what probability does this kind of a maximum load occur? So that's the kind of question which we are interested in. And actually, this was from the lectures also. Yeah, you can see the lectures. So the final claim comes out to be that the probability uh, that with probability at least 1 minus 1 over n, every bin has at most 3 log n over log n uh, number of balls. And the expectation of the maximum load is like a 3 log n over log n plus 1. So approximately uh, this would be the maximum load if you like toss these n balls uniformly randomly into something. Because with so this is the expectation, and with very high probability, actually the load is almost this one. So yeah, and for the derivation of these results, of course, you can refer to the lecture at any point of time. And then after this, a very beautiful, like, I find this concept very beautiful. The concept of 2-point sampling was discussed. And what's the 2-point sampling technique? So, like, on a very high level, like before coming to the discussion, the idea is that, okay, like, so far, for these questions and everything, what we are assuming is that we have some kind of a uniformly random distribution from which we are able to sample our random variables. But note that in the real world, randomness is not free. Like it's not like you can just ask anyone about like you can just ask anyone, okay, that give me some random bit and they'll be able to give you like computing random bits is a like obtaining these random bits is computationally expensive. So what you want is so the source of so essentially the source of randomizations in computations are like quite expensive. So what we usually want is that we want to minimize the number of times we have to make a call to these kind of to obtain these kinds of random bits. So we want to use randomization as little as possible. And this is captured by this notion of utilizing a little number of random bits or like calling this random oracle to give us a some random bit like a few number of times. So, and this 2-point sampling is one of the techniques which is used to decrease the number of uh, random bits used by an algorithm. So of course, this is not like a strategy which works always, but yeah, it is a quite general strategy, and yeah, it's really nice. So so it's a general notion. So we are not pertaining to any specific problem. Uh, but let's see what this says. This 2-point sampling says. So let pi be a problem and A be a randomized algorithm for pi. And suppose A has one-sided error. What does one-sided error mean? One-sided error means that yeah, that the algorithm always outputs correctly for yes instances. That like uh, if the instance is if the algorithm outputs yes, then the instance is actually a yes instance. And if an algorithm actually outputs no, then the algorithm outputs correctly with the probability just half. So what can happen is, so if the instance was yes, then the algorithm was correct. But if the instance was no, then also the algorithm can sometimes output yes, and it can answer output sometimes no, which probably happy. Let's say you want to boost the success probability of this algorithm from half to 1 minus poly log n. Suppose 1 minus 1 over poly of n. Suppose 1 is not such as okay, that suppose someone comes and says to you that okay, this algorithm is kind of useless because it is if it outputs no, then I really can't be sure if the algorithm is correct because like uh, because this probability half, or let's say half plus epsilon, is really not that good of a guarantee. And suppose you want to say, okay, no, that this algorithm, you want to get a better idea of what the output is. So what you can do is you can run this algorithm multiple times. And what's going to happen is if you run the algorithm multiple times and you say that hmm, the instance is a no instance if any run of the algorithm outputs no. So the probability of error, what would be the probability of error in this case? It would just be that okay, so you're now running the algorithm k times. So the probability that the algorithm is wrong on the first attempt is half, is wrong on second attempt is half, is wrong on the third attempt is half, and till fifth attempt is also half. So this is and since these are independent events, so you will multiply their probabilities. So that probability that the algorithm makes an error after we have like k iterations of the algorithm. Uh, so suppose for k iterations, the algorithm keeps saying that the instance is a yes instance. Then it's very likely that the instance is actually a yes instance. And the probability with which the algorithm will say that the instance is a no instance when it is uh, actually a yes instance will be the probability will be this, the probability of error. And we know we need that, yeah. Usually what we want is we want these probability guarantees to be the error guarantees to have very low probability, 1 over polynomial in n because polynomial in n because usually we assume that n is very large, so this quantity becomes very small. And if you want this 2 to the k to be approximately poly n, then how much do you have to choose the value of k to be? So this is just high school math that you will have k to be some constant times log n. And then if you put some constant times log n here, then you'll have 1 over poly of n kind of a probability. So yeah, so this is all very nice that if we have a algorithm which had a probability of success probability of half, we were able to boost its probability to really big, really nice form. But we are doing this at the cost of what? So we are doing this at the cost of running the algorithm multiple times. And if we are running the algorithm multiple times, since the algorithm is randomized, we'll be using a lot of random bits. So suppose the algorithm A originally uses some D random bits. Then if we are running the algorithm K times, then the number of bits which we'll end up using will be D times K. Uh, so so essentially what this is that, and note that you need this K to be log n, or you need this K. The more you increase this K, the better will be your probability guarantees. So to improve the probability guarantees, actually you need more random bits or more randomness. And yeah, since this randomness is computationally expensive, so this kind of creates a dilemma for us. We need to trade off correctness with computation power. And this is where this 2-point sampling technique comes to the rescue many times. That what one can do is instead of using these DK random bits, one can just uh, so two in this 2-point sampling technique actually provides idea so that one just uses 2D random bits instead of D times k random bits. So using 2-point sampling, like you can run the algorithm k times, but you'll just be using 2D random bits instead of d times k random bits. And what does the high level idea look like? So it's instead of sampling these k random strings, these these d length random strings k times for the k executions of the algorithm, what we do is we just randomly sample two strings of length d each. So we have just sampled like 2D bits instead of DK bits. And now what we are going to do is in any run of the algorithm, we are going to construct a new, like not exactly random, but close to random string using these R1 and R2 strings. So we are not going to again ask the oracle for another random string. We are just going to uh, yeah, use these strings to create the strings which are not exactly random but sufficient but suffice for our purposes. And how are we going to define the string? So let's say for like if we want to define t such strings, t random strings, then for any string sj can just be defined as like r1 times j plus r2. And yeah, so and these s1 till sgs are the strings which we'll actually use for uh, the randomness required in our algorithm. So instead of like computing this R1, R2 till Rk, we'll just ask for this R1 and R2, and we'll simulate these k random strings using just combinations of these R1 and R2. So yeah, and actually it can be proven this was shown in lectures also. So yeah, we won't be getting the proof of this, but one can show that uh, that this in this technique what we do here gives us uniformly distributed and pairwise independent random variables. So it's not like we are just doing this out of the blue. We need to actually mathematically prove that what we are doing actually gives us some random bits, because random bits are essential for the functioning of our algorithm. And one can actually prove that, oh, this procedure ends up giving us random bits, and which suffices for the purpose of our algorithm. And so essentially what happens is instead of like k times g random bits, we have just run the algorithm k times using just 2D random bits. So it's like a huge improvement, like by a factor of k improvement. And k is like a Boolean, or like you can even increase it as much as you like to boost the success probability of your algorithm. So this is pretty nice. Yeah. And after this, in the lectures, we also discussed randomized algorithm for the two-set problem. So what is the two-set problem? So in the two-set problem, suppose, so I hope people have heard of this, like two-set is this two satisfiability problem. And what does this mean? So suppose we are given a two-set formula as input with m clauses and n Boolean variables. So what do we mean by clause? Uh, and what do we especially mean by these two sat clauses? So clauses are essentially uh, uh, Boolean variables are separated by ORs. So this L1 or L2 is one clause, this L3 or L4 is another clause, and so on. So, and in this two-sat problem, essentially, there are just two literals in every clause. So if there is like X. So every clause will be of the form X or Y in a two-sat problem. And all of these clauses are like in the sat problem joined by these AND clauses. This is L1 or L2 and L3 or L4. Similarly, this is also a two-set problem, x1 or x2 bar and x2 or x3 bar and x3 or x1. And then for this two-set problem, so I think a lot of you may have heard of this three-set problem, which is like NP hard problem, not like NP complete problem. But note that actually two-set problem is not NP hard, like it's solvable in polynomial time. So suppose one has to answer that if this formula f satisfiable. Suppose you are given this two-set formula and the problem asks us, is this formula f satisfiable? And actually it turns out that, like I said before, the two-set is polynomial time solvable. And the idea for like a randomized algorithm for two-set, there exist deterministic algorithms also, but since we are discussing randomized algorithms only, so we'll be just sticking to that for now. So the idea is pretty simple and like pretty cute also that suppose one just picks a uniformly random assignment for the variable gx until gxn. So yeah, so you just put like for these all these variables in the Boolean formula, you just put them uniformly randomly as like true or false, and you try to see whether the formula is the two-set formula gets satisfied or not. And while the formula is not satisfied by the current assignment, then just let's just find a clause which is not satisfied by G. Suppose C is the clause which is not satisfied, and suppose C involves the variables xi and xj. Then pick xi and xj, one of these xi and xj uniformly at random. So with probability half, you'll end up picking xi, and probability half, you'll end up picking xj, and you just negate it. So what you do is suppose your random output was like xi. Suppose you picked xi, and xi was initially set to true in this formula G. So now you will set the xi to the false, because what this ends up doing is then the formula will then this clause, at least the clause C, will at least become satisfied as soon as you negate one of the variables of the formula which is not satisfied. And now you keep repeating this process till something like n times, where n like is some kind of a threshold. Like if you have repeated this process for some threshold number of times and still you are not able to find a satisfying assignment to the two-set formula, then it is very likely that actually the initial function is not satisfiable. And if like actually you can mathematically prove it, was shown in the lectures also. So essentially, you can show that this kind of like a randomized algorithm which randomly selects a clause and just which selects a clause and just randomly flips its bit. This kind of algorithm will find a satisfying formula if it exists in some threshold number of iterations with high probability. And what are these thresholds? So threshold is lambda times n square, and runtime is order n square. And what is lambda? So lambda is the error probability. Like so, if you are saying the formula is not satisfiable, then with what probability are you saying that the formula is not satisfiable? And the error guarantee is like 1 over lambda. So intuitively also you can see that so threshold is the number of iterations and error is 1 over lambda. So intuitively you can see that the more you increase the iterations, if the number of iterations increase, then essentially intuitively you have tried more formula. And if you have tried more formula and still have not found a satisfying assignment, then it is more likely that the original function f is unsatisfiable. So if you increase the threshold, the probability of error decreases. And this is what's happening here also, that if you increase the threshold, it means you're increasing lambda because this n is fixed for a problem. So, but this lambda is a parameter of R choosing. So if you increase this lambda, then the error probability actually goes down. So if you want this lambda to be like, let's poly n or just n, then you have a like a n cube iteration algorithm, which has an error of just 1 over n. So something like this. But if you just want a constant probability, then yeah, this is just a constant probability. Like this is a order n square n time algorithm. So yeah. Okay, so I hope this makes sense. If it makes sense, then maybe we can yeah, maybe then we can move over to the some of the questions which I had prepared. So actually, like I had not prepared a lot of questions because in the last session, actually, we spent a lot of time discussing the theory. Uh, but yeah, in this session, I guess many of you are not, and none of you is present live in the session, so that's why, yeah, we don't have any doubts in the theory or like. yeah, we don't have anything concepts to clear. This is where majority of the time was spent in the last session, so I planned accordingly, but it turns out, yeah, this time we should have had more questions. But nonetheless, we can discuss the questions which we still have. So, yeah. So, yeah. Okay. So, this first question actually, so maybe I'll leave the first question till the end. So, first question was the question which I had actually given as a do it yourself kind of an exercise last time. So, like why am I doing this? Because anyways, this is like relevant to uh, the randomized algorithms kind of a thing. So yeah, I think so. The question was like, suppose you are given this quick select algorithm. So we discussed in the lectures the quick sort algorithm, but suppose you are given this quick select algorithm, then we have to prove that the expected number of comparisons of quick select is just not array. So yeah, so so I gave this as a homework kind of a thing, or do it yourself, but maybe if the time permits today, I think it will. Then we can also discuss how do you go about this? Because I think it's a really cute problem. But let's leave it for the end. And yeah, so maybe before starting with the problems, maybe let's just break for like 5 or 6 minutes. Maybe I can get some water in the end, and hopefully before someone joins the session in person uh, in the next like let's say 5 6 minutes. Uh, like so that at least they can attend the problems. If no one joins, then anyways, like we'll start discussing the problems in the next 5 6 minutes. So till then, I'll just mute myself. Okay, so since no one else has joined the session, I guess we can get started nonetheless. We should just start with the problems. Anyways, so yeah, so maybe let's just start with what's a good problem to start with? Yeah, maybe let's just start with the third problem first. Uh, so suppose the problem says that let x be a geometric random variable with parameter 0.1. What is the expectation of x? So I hope everyone is familiar with what are geometric random variables. If not, like essentially what the problem is saying is that hmm, the problem is essentially saying that uh, the parameter is so suppose yeah, so what's a geometric random variable on a very high level? I hope everyone knows, but still I'll just describe it totally. Suppose this parameter is some p, then the geometry random variable essentially says that, okay, what this parameter p means is that suppose you're tossing a coin, and suppose heads comes up with probability p, and tails comes up with probability 1 minus p. And then uh, geometric random variable says that how many times will you have to toss the coin, like uh, so to obtain heads for the first time. So like it is possible that like you obtain heads after 5 trials. So what's the probability that you obtain heads after actually 5 trials, or like you obtain heads the first time on the fifth try? Similarly, like the so this random variable, like this x random variable takes the value 1, 2, 3, 4 till infinity, and the probability associated with, like, let's say x equal to 1 will be the probability that x takes the value like will the probability p, because x takes the, like, the heads comes up on the first try with probability p. So essentially, like if p is the parameter for a geometric random variable, then what's the expectation of x? So expectation of x is nothing but the probability. So it is just 1 multiplied by the probability that x equals to 1 plus 2 multiplied by probability x equals to 2, and so on. 2 multiplied by, so what's the probability with which heads comes up first time on the second try? So we have used 2 tries, so like we multiply it by 2. Similarly, plus 3 times x equals to 3, and this goes on till infinity. So yeah, plus dot dot dot. And what is this equal to? So this is nothing but as I just described. So what's the probability? Okay, maybe I should also describe. So what's the probability, like x equals to I? What's the general formula for probability x equal to I? So this is just that like so what's the x equal to I does what does x equal to I mean? So x equal to I means that you have obtained, like for the first I minus 1 trials you actually obtained tails, and on the I trial is the first time you are obtaining heads. So for the first I minus 1 trials you obtain tails. So for this is with probability 1 minus p raised to the power I minus 1. And then with probability p on the I trial, you actually obtain heads. So this is something, yeah. So this is the probability that x equals to y. So what does this mean? So first time I equals to x equals to 1. So we put I equals to 1. So here it's just 1 times uh, 1 minus p raised to the power 0 times p. So it's just 1 multiplied by p, plus the second term will be 1 minus p times p, and this will multiply by 2. So 2 times 1 minus p times p. Yeah, maybe I should write it times p. Yeah. Okay. Or maybe just like, yeah, it's anyway. Shit, understand. Yeah. So 1, 2 times 1 minus p times p plus 3 times 1 minus p squared. So this will have a square now, and this will be 3, and this will be, yeah, times p. And yeah, so this will, maybe I should, yeah, I guess it's fine. So yeah, I just don't want to create confusion of this. Where what is this star? What does this star mean? So it's something like this, and plus 4 times 1 minus p cube, and so on. So this goes on. And how do we find the sum of this? So this is actually not very hard to do. This is something which you have already learned in high school, which is something called a AGP, because the coefficients are in AP 1, 2, 3, 4, and something, and these products are multiplied by this 1 minus p factor. So there's an arithmetic geometric progression. And actually, if you simplify this formula, it comes out to be just quite simple. It comes out to be just 1 over p. Yeah, it just comes out to be equal to 1 over p if you do the calculations right. And so what essentially this means is like, yeah, for any geometric random variable with parameter p, the expectation of x is just equal to 1 over p. So in the given problem, mhm, since p equals to 0.1, hence expectation of x is nothing but 1 divided by 0.1, which is nothing but 10. So 10 is the answer to this question. So essentially, in expectation, you need 10 trials so that you obtain heads for the first time. Okay, so if this is clear, then maybe we can move on to the second question. Why I wanted to do the third question first and second question later, although similar problem has been discussed in the lecture, this is because like the second problem uses kind of the same idea as the third problem. So the second problem says that consider the coupon collector problem with 50 coupons. What is the expected number of times we need to draw to see 3 coupons? So this is somewhat similar to what was discussed in the lectures. If we have seen the lectures and understood them, this problem should be not too hard. So yeah, so maybe like let's just denote by a random variable x, the times, let x be the random variable denoting the number of times we need to draw to see 3 coupons. And similarly, we'll also define some helper random variables. We'll be trying to use linearity of expectation and all, because we discussed about this last week, also the power of linearity of expectation, and also we have to be comfortable with it because this has been discussed somewhat in the lectures also time and time again. So let xi be the random variable denoting the number of times we need to draw to see ith distinct coupon, given that we have already seen I minus 1 coupons. So suppose we have already seen I minus 1 coupons, then let xi be the random variable denoting the number of times we need to draw to see the ith distinct coupon. Okay, so what we can say is what is x equal to? So x is nothing but x is the number of times we need to draw to see 3 coupons. So for seeing 3 coupons, what we need to do is first we need to see the 1 coupon. And after we have seen the first coupon, after we have seen 1 coupon, we need to see another coupon. So first we need to see 1 coupon. So x1 will denote the number of times we need to draw to see 1 coupon, which is distinct. And then after we have drawn this 1 coupon, then the extra number of times which we'll need to draw to see the second coupon after we have already seen this coupon will just be x2. And then we will need to draw another time uh, x3 because we have already seen 2 coupons and now we need to see the third coupon. So this will be the case. Uh, it can be seen that x is equals to this. And also what one can say about this problem is that what will be the expectation of xi. So what will be the expectation of xi? So this was also discussed or maybe yeah. So maybe not like this, but yeah. So what's the probability that let's say the random variable xi is some value, takes some value k. So what's the probability uh, that the random variable xi takes the value k? Like the number, so k is the number of times you need to draw to see the I distinct coupon, given that we have already seen I minus 1 coupon. So uh, actually note that suppose also maybe we can just have like x1 for now. Okay. Okay. Uh, yeah. Uh, One thing is to see that that expectation of also x1 equals to 1. Uh, yeah. One thing which we need to see is that x1, the variable x1, so x1 is nothing but the number of coupons which we need to draw to see one distinct coupon, given that we have already seen 0 coupon. So we have not seen anything, any coupon we draw will be a distinct coupon. So x1 will always be equal to 1. Mhm. Mm. And what's the deal with x2? So what's the deal with x2? So probability that let's say x2 takes some value k. Suppose we need to draw let's say k coupons uh, to see the second distinct coupon. What will be this probability? So note that if we have already seen 1 coupon from x1, then there are now 49 coupons available from out of these 50, which will result in the second coupon being distinct from the first coupon. So with what probability? So if k time is the first time which we have seen the uh, distinct coupon, the second coupon is distinct, then it means that for the first k minus 1 times we would have just seen this x1 only, the coupon chosen in the first try. So and with what probability is this coupon chosen? Since coupons are usually formed randomly, so this coupon is chosen with probability 1 over 50. And this is for like the rest of the k minus 1. Sorry. And then, yeah, and out of the remaining 49 by 50 coupons, uh, we need to choose one of the coupons. And does this kind of a formula remind you of anything? Like probability of x2 equals to k is something like this. So this is nothing but what we just discussed, that this is just a geometrically distributed, so x2 is just a geometrically distributed random variable where the parameter p is nothing but equal to 49 by 50. So hence x2 is a geometric random variable with parameter 49 over 50. Uh, this implies that expectation of x2 will be nothing but 1 over p, which is just t over 49. So I hope this makes sense. And uh, similarly, what one can say is that if we are now trying to find out x3, so for x3 now we have already seen two coupons, and now we need to find that the number of times we need to pick the coupon so that the third so that we pick the pick a coupon which is distinct from the first two coupons. So what will be this equal to? So maybe I'll just copy the observer formula. Yeah. And so what's the probability that x3 equals to k? So here now we can have like any of the two coupons which we have already seen, and will be in the failure case. So here it will be 2 by 50. And now there are 48 new coupons which we can see. So this will be like 48 by 50. And now this is x3 is a geometric random variable with parameter 48 by 50. And what this implies is expectation of x3 is nothing but 50 divided by 48. So now we have so x1 is actually equal to 1. So expectation of x1 is also equal to 1. So if something is 1, then its expectation over any probability is also 1, right? Uh, so yeah. And now, so we have expectation of x1, we have expectation of x2, we have expectation of x3, and what we needed to find out was expectation of x. So by linearity of expectation, expectation of x is just summation of expectation. So by linearity expectation expectation of x is nothing but expectation of x1 plus expectation of x2 plus this plus expectation of x. And this is nothing but 1 plus 50 over 49 plus 50 over 40. Yeah, you can compute whatever the answer this comes out to be to the closest decimal. But this is the yeah correct answer. Okay then. So after yeah, so this is the final answer. So after discussing this, yeah, then so we have discussed the second question as well as the third question. So now let's discuss the fourth question first. So this is again, yeah. So this is related to the load balancing, so not exactly, but yeah, quite similar. So the problem says that suppose we have five balls, and now we are not distributing them into five bins, but let's say just three bins uniformly randomly. So we have these five balls and we throw them uniformly randomly into, let's say, three bins. Then what is the expected maximum load of any bin? So, so we are given these five balls, which we are throwing uniformly randomly into these three bins, and now we need to find the expected maximum load of any bin. So, so what's the like max expectation of the maximum load? This is what we need to find. Okay. So, for this problem, how can we approach this problem is, yeah, one way is through combinatorics, but I'm thinking of how to describe it in terms of probability. So, so okay, so maybe we'll need anyways, probabilities. So, okay, guys, so So let's see, like, if we have to find the expected maximum load of any bin, let's see how these 5 balls can actually go into 3 bins. So, how the 5 balls can be distributed into the 3 bins. And these 3 bins are, let's say, distinct. So 3 bins are distinct actually. So, so how can they be distributed? So the first way can be uh, like the first bin has 0 balls, second bin has 0 balls, and the third bin has 5 balls. Yeah. Uh, or like any other permutation. Like, yeah, maybe it's better to have 5 plus 0 plus 0, or 0 plus 0 plus this, or yeah. So one of the bins has all the 5 balls, and yeah, no other bin has any balls. So this is one way in which the balls can be distributed. What's the second way in which the balls can be distributed? So one of the bins has 4 balls, another has 1 ball, and so on. So 4 plus 1 plus 0, or yeah, and this one can also be like in some other. So this question involves a bit of calculation or casework, and but yeah, I think it's necessary in this question. If anyone comes up with a better argument, then yeah, please inform me in the next session or in the comment. So either the first bin has 4 balls, or let's say this, yeah, or let's say the second bin has 4 balls. So let's say the second bin has 4 balls, then first bin can have 1, and third can have 0, or uh, first can have 0, third can have 1. And then we have like the third case where the third bin has 4 balls. And then also we have these 2 cases. Yeah. So these will be like 6 cases here. 1, 2, 3. Maybe I should write this R in capital so that it becomes a bit more dividing the case. So now we have 1, 2, 3, 4, 5, 6 cases here. And now what's another way in which these balls can be distributed is something like if the maximum number is not 4, but the maximum number is 3. Like the balls are distributed into the 3 bins, and like the maximum load of any bin is just 3. Then what's the way? Like either you have like 3 plus 2 plus 0, or let's say the first bin has like 3 balls, the second bin has 0, third one has 2. Similarly, one can have like first bin has maybe let's say the second bin has the 3 balls, and so the first bin, let's say, has 0, second bin has 3, third bin has 2, and similarly first has 2, second has 3, and third has 0. And similarly, if the third bin has 3, then between first and 2 there can be zeros or 2s. So 0 plus 2 plus 3, or 2 plus 0 plus 3. And what's another way? So another way is just, yeah, the maximum is 3, but now the balls are distributed as 1 and 1. So 3 plus 1 plus 1. And now there are the three ways. Uh, one, 1 plus 3 plus 1. Yeah. And 1 plus 1. And now I think there's just one more way. So if the maximum number of balls allowed is 2, then actually one can only have again like these kinds of ways. So 2 plus 2 plus 1, or mm, uh, yeah, 1 plus 2 plus 2, or 2 plus 1 plus 2. So these are the only ways in which the 5 balls can distribute to 3 bits. So just to see if, for you guys explicitly, I wrote down these all of these cases. But yeah, one can do a bit more smart. One can be a bit more smart and count these cases directly using like yeah, combinatorics. But just for like so that everyone is on the same page, I try to show all of these explicitly what will these cases look like. And now note that there will be no other case because if the maximum size of any bin is 2, then this is the only way. If the maximum number of balls in any way is 2, this is the only way in which this is the only way in which the ball can go. And note that the maximum bin size cannot be less than 2 because the maximum bin size is 1. Then there are just 3 bins, and you cannot have more than 3 balls. But what we have are like these 5 balls. So yeah. So these are the number of ways, and so now, so what's the probability that case one occurs? So probability of one. So what's the probability of one? So so essentially, like, what will be the expected maximum load of any pin? The expected maximum load will be like, so in these cases, the load is 5. So 5 times the expected probability that this case occurs. So only 4 times the probability that this case occurs, plus 3 times the probability that this case occurs, plus 3 times the probability that this case occurs, plus 2 times the probability that this case occurs. So now what's the probability of case 1? So probability of case 1 is this. So the ball has to be like these, like 5 plus 0 plus 0, or 0 plus 5 plus 0, or 0 plus 0 plus 5. So that each ball goes into any of the three bins with probability 1 over 3. So what's the probability with which all the balls go to the first bin? So going to the first bin has a probability of 1 over 3. So all these balls are going to the first bin. So this the probability is like 1 over 3 mm, raised to the power 5. And note that there are 3 such bins. So yeah, so it will be like 3 times 1 over 3 raised to the power 5. Because this case, all of these have 1 over 3 to the power 5 probability. And now moving on to yeah, the probability of the second case. What does the second case look like? So in the second case, 4 balls are so the 4 balls are going into one bin, and the fifth ball is going into some other bin, right? So what's the probability that this happens? So note that there are 5 balls. So first you have to choose which 4 balls are going in. So first of all, like there are 6 cases, so we can easily multiply 6 in the front. And after that, if we are looking at any of the cases, so in this case, like what's going to happen is, so there are 4 balls in the first bin and 1 ball in the second bin. So, but there are a total of 5 balls. So, which 4 balls are going into the first bin? We'll have to do it by choosing out of these 5 balls, we'll be choosing some 4 balls. And these 4 balls will be going into the first bin. So, with if I choose 4 ways, we select these 4 balls. And I hope you guys remember combinatorics. Yeah, what does this notation mean? Because I assume that you know this. And now these 4 balls have to go into the first bin. So this go into the first bit is the probability 1 over 3. right? And this raised to the power 4. And now the fifth ball has to go into the second bin. So again, with probability 1/3. Yeah. So this is the probability of case 2. And then what's the probability of case 3? Yeah, so the probability of case 3. So there in 3 there are again like 6 cases. So we just multiply it by 6 directly. And now 3 balls are going into one bin, 2 balls are going into the second bin, and so on. So yeah. So uh, what we do is we select out of these 5 balls, we select the 3 balls which will go into the first bin, and yeah, and these go into the first bin with probability 1/3. Yeah, and so it's like 1/3 raised to the power 3, and then the remaining 2 balls go into the second bin. So with probability 1/3 raised to the power 2. Yeah. So this is the probability of 3, and now let's go to probability of 4. And what's the probability of 4 look like? So in this case, what we are doing is, yeah, so there are 3 cases. So let's distinguish there are 3. And now we have to select 3 balls which go into the first bin. So from the 5 balls, again, we choose 5, choose 3 balls. And these balls are going into the, let's say, first bin. So we send these into the first bin. Yeah, so they're going to the first bin is probability 1/3 Q. And now what's going to happen is, so now we have 2 balls remaining. But note that from these 2 balls also, you have to send one of these to second bin and one of these to the third bin. So you'll have to choose from these 2 balls one of the balls. And you'll be sending one of those balls to, yeah, the uh, second bin and one of those to the third bin. So you send this to 1/3, and the third ball you just send to the third. Yeah, it's again 1/3. Yeah, so this is the idea. And now what's the probability of the fifth case? So in fifth case, there are 3 cases. So there's 3 cases, and what are the probabilities? So we have to select 2 balls. So maybe I'll just copy paste from much easier. So yeah, and now I'll make the edits. So we just have 2 balls. So we have to first select 2 balls. So the case was 2 plus 2 plus 1. So first we select 2 balls, and now these 2 balls will be going into this one into the first bin. So we will do 1/3 squared, and then out of the remaining 3 balls, we have to select again 2 balls which go into the second bin, and they go with probability 1/3 squared. And then we just have a remaining 1 ball, and it will go into the last bin with probability 1/3. Right. So these are the probabilities which we have obtained. So this is nothing but, so I'll just take 1/3 raised to the power 5 as common in all of these. So this is just 6 times 5, which is 30. So this is just, so this is, maybe I'll just copy this and change the coefficient in every term. So this is just 30. And this is going to be, yeah, maybe I'll just, this, yeah. And this is, the coefficient is just 1/3 raised to the power 5. This is 5 choose 2. 5 choose 2 is, 5 choose 2 is nothing but mm, 5 into 4, 10. So this is just 60. Because 5 choose 2 is just 5 times 4 divided by 2, which is 10. So 10 times 6 is 60. And here it's just again 5 choose 3 is like again 5 choose 2, and it's like 5 into 4 divided by uh, 2. So it's just 10. So this is 30, and this is 30 times 2, which is again 60. And what is this equal to? So this is just 3 times 5 choose 2. So 5 choose 2 is nothing but 5 into 4 divided by 2. So this is 10. So 10 times 3 is 30. So this 3 times 3 is 9. And 9 times 10, 90. This is just 10. Okay, I think I made some pretty bad mistake here. Or is it correct? So if this is 90, mm, yeah, 90, 152, 100. Yeah, it's right. Oh yeah, it's correct. So note that so we have these probabilities of all of these cases, and like just for a sanity check, we would like to say that okay, these cases were exhaustive, so the probabilities should sum up to 1. So note that 1 by 3 raised to the power 5 is just 1 over 243. So these coefficients should sum up to 243. So it's like they indeed do. Like 30 plus 3 is 33, 33 plus 60 is 93, 93 plus 60 is 153, 153 plus 90 is 243. So the probability sums up to 1 actually. So this is right. So now we have to find actually the expected number. So we had to actually find the expected maximum load of any bin. So note that in the case 1, the maximum load is 5. And this occurs with probability this much. So yeah, so expected max load is nothing but so in the case 1 we have a load of 5. So 5 times probability of 1. So I'll just write now case 1. Probability of 1. Yeah, for now I'll just write it like this. And we'll substitute the values later. And then for case 2 uh, we had the maximum as 4. So for case 2 we had the maximum as 4. 4 times probability of case 2, and similarly 3 times capacity of case 3, and again 3 times the probability of case 3, case 4. Because in case 4 also the max capacity was 3. And then in case 5 we had a capacity of 2. So yeah. So this is the answer. And what's this equal to? So just putting in the values. So what was the probability of 1? So 1 by 3 raised to the power 5 comes out to be common for now. And the remaining things, so maybe I'll just put this in common. So 1 by 3 raised to the power 5 multiplied by, yeah. So what does this come out to be? So this is, probability of 1 is 3. So the coefficient is 3. So 3 times 5. So 5 is multiplied by 3 plus, or case 2 we had this 30. So 30 times 4. This is 4 times. So this is 4 times 30 plus 3 times 60 plus 3 times 90
Oh, no, again 360, sorry. 3 times 60, okay, and plus 2 times uh, 90. So yeah, so this is a final answer, and this will be approximately so yeah, let's just try to see what this comes out. So again, so 5 times 3 is just 15. Maybe we just do the calculation. 15 plus 4 times 30 is 120, and 3 times 60 is 180, 3 times 60 is 180 again. Oh, and 2 times 90 is also 180, that's fine. So we have 180 plus 180 plus 180 is just 540, and this will be 540, 640, 660, 660 plus, yeah, maybe I'll just, yeah, so till now I had obtained this 660, this was 15, uh, so this comes out to be 675. So yeah, so this is the answer. So this is just 675 divided by 243 is the answer. And can we simplify this further? I think yes. So both of these are divisible by 3, so this becomes 225 divided by 81, and I think this can simplify it further. So if you multiply it, so this is divisible by 9, this is divisible by 9, so this is just 25 by 9. Yeah, so maybe I'll just write it directly. Yeah. So 25 by 9 is the answer. Yeah. So then the expected maximum load is equals to 25. And for sanity check, you can also see that the maximum load should have to be at least 2, because like because in all cases, like at least a load of 2 is needed. The expectation will always be at least 2 in that case. So yeah, so this resolves the problem, and yeah, this is what we obtain. Okay then. So maybe yeah, yeah, I don't think so actually, like in the calculations of these questions only a lot of time went away. So I don't think uh, we should be starting with this question again. But maybe I'll just for so I won't be discussing this the first question fully, but I'll just maybe give some more hints. So I'll assume that you guys have like looked at the question beforehand also, because I gave it as a like do it yourself exercise last week also. Essentially, we are trying to find median of an array using an algorithm called quick select, where we are just picking a pivot element uniformly at random, and we see whether and we like as we do in quicksort, we scan the array and move the element smaller than the pivot to the left, larger to the right, and see if the pivot is at the median position or if pivot is at the left of the median or right of the median, and we search in the corresponding subarray accordingly. And this comes out to be the expected number of comparisons to find out the actual median comes out to be order log order n, linear. So yeah, how does this happen? So maybe I'll just give a hint too. So maybe this is again still a do it yourself. Maybe this if this hint was not sufficient, then maybe yeah, this is just a hint one, and hint two is uh, the cases will look like this. Okay. So hint two maybe consider yeah consider an indicator random variable xij. where xi, which takes the value 1 if I and j are compared in the run of the at any point in the run of the algorithm. Else 0. And like this is similar to what we see in the quicksort. Then uh, expected number of, okay, then total number of comparisons is equal to uh, some, okay, maybe I should, yeah, yeah, so some overall possible xij, and yeah, so some overall possible xij will be the total number of comparisons. So we just need to find out, hence the main task is to find out expectation of xij. But note that here expectation of xij will not be that trivial as it was in quicksort. Like in quicksort also it was not trivial, but here it will be a bit more difficult. And maybe another hint, like to find out expectation of xij, uh, uh, let the median of the array be n. Uh, Then to calculate expectation of xij, consider the following three cases and find out expectation of xij accordingly. And what are the three cases? So first case will be case one will be okay. If and here the ij elements are in the sorted array, like ith and jth elements in the sorted array. So like how do you sort that ij elements in the sorted array are compared at any point? So case one is actually mm, maybe mm, let the median be m ith element. Okay, yeah, or maybe yeah. Okay, maybe we don't need this. Yeah. So there will be three cases, and we need to deal with them separately. That so median is in the n length array. The median is n by 2th element, approximated n by 2th element, right? So suppose one case is that the value n by 2 is less than I is less than j. So we'll always be assuming without loss of generality that I is less than j. Case 2 will be that this n by 2 is between I and j, and case 3 would be that is greater than this thing. And in these three cases, actually, you will have to find out. You'll see that in some cases, like the calculations will go differently. And when you sum over these, you'll see that actually there why you don't obtain the n log n kind of thing, but n order n kind of a thing. But yeah, this is the maximum hint which I can give. Otherwise, I'll just be giving away the whole solution. So yeah. Okay, so I guess so today in today's session, I guess yeah, this kind of hint is sufficient. So I believe now you'll be able to solve this question. So apart from this, we discussed like three questions, and we discussed the calculation in quite a bit of detail for these questions, and we also discussed all the in the session, all the uh, things discussed in this week's lectures on a very high level, and this week's was mostly on like applications of concentration bound. So yeah, so I guess we are also almost out of time. So since no one is present in person in the session anyway, so uh, there won't be any doubts. So I guess I'll just close the session then. And hopefully I'll see you guys next week in person, actually. Same timings, Tuesday, 6 to 8 p.m. So till then, see you guys and all the best for the assignment. I'll just close the session now. Thanks for attending. Thanks for watching the session.